Hello friends, I welcome you in lecture number 2 on Chebyshev's inequality. In lecture number 1, we have discussed about Chebyshev inequality and we have seen two forms of Chebyshev inequality. And we know that if a capital X is a random variable with mean mu and standard deviation sigma, then probability that capital X minus mu greater than or equal to k times standard deviation sigma is at most 1 by k square. That is 1 by k square is the upper bound for this probability. And another form is the probability for complementary event of this event, that is probability that x minus mu is less than k sigma. This probability can be greater than or equal to 1 minus 1 by k square. That is lower bound for the probability of this event, absolute value of x minus mu less than k times standard deviation sigma is greater than or equal to 1 minus 1 by k square. That is 1 minus 1 by k square is the lower bound for the probability of this event, and 1 by k square is the upper bound for the probability of this event. So in the question you have to decide that whether you are interested in the lower bound or upper bound, and then you have to use appropriate form of Chebyshev's inequality. And here we are going to discuss one problem related to this Chebyshev inequality, and this problem was asked in GTU Summer 2021 exam. First we understand this question. A fair dice or die is thrown 300 times. Find the lower bound for the probability of getting 40 to 60 sixes. So here experiment is throwing a fair dice 300 times. That is the number of trials, which we denote by small n, is 300. And suppose random variable capital X denotes the number of times 6 appears when we are throwing a dice. There are 6 possibilities and we are interested in the number of times 6 appears on the upward face of a dice. So we consider our random variable as the number of times 6 appears, and here they are throwing a dice 300 times. Now there are 2 possibilities for each of these trials, because we are throwing a fair dice, that either 6 appears or 6 does not appear. Suppose we consider success as that 6 appears, or getting a 6 is the success, then we know that probability of getting 6 is 1 by 6, and we denote the probability of success by small p. And here number of trials are finite. There are only 2 possible outcomes for each trial, that whether 6 appears or 6 does not appear, and probability of success remains constant for each trial, and therefore this capital X is a binomial random variable, or this distribution of the number of times 6 appears is a binomial probability distribution. And we know that the mean and standard deviation or variance have ready-made formula if our probability distribution is binomial distribution. So here we first mention that here capital X is a binomial random variable with parameters. N is number of times we are throwing a dice, that is number of trials, and probability of success is 1 by 6. Therefore mean of binomial distribution, we know that mean of binomial distribution is obtained by multiplying number of trials with probability of success, that is n times p. So 300 times 1 by 6, and this is nothing but 50. Therefore mean is 50, and variance of binomial distribution is given by n times p times 1 minus p. That is, n times p is 50 into 1 minus 1 by 6. That is 50 times 5 divided by 6, and using scientific calculator I find this as 41.6667 up to 4 decimal places. And we are interested in this value of standard deviation, which is nothing but square root of variance, and square root of this quantity is 6.4550. So if mean and variance are not given, you can find them by identifying that given random variable is any special random variable or not. If our random variable is not any special random variable, then they will provide the either probability density function PDF or probability mass function PMF, and using the formula of mean and variance you have to decide what is mean, mu and variance, because to use Chebyshev's inequality we must have the values of mean and standard deviation or mean and variance. So here they are not given, but we find that given random variable follows binomial distribution, and we have ready-made formula for the mean and variance of binomial distribution, and using those formulas we are able to decide mean and standard deviation for given random variable. Now here we have to find the lower bound for the probability of getting 40 to 66. That means we have to find that what is the lower bound for this probability of getting 40 to 66 is, that is capital X is in between 40 and 60. We have to decide the lower bound for this probability that capital X, which is the number of times getting 6, is from 40 to 60. That is, capital X is in between 40 and 60, and here we are asked to find out the lower bound. Therefore we will use this inequality, this form of Chebyshev inequality, that is probability of x minus mu less than k sigma is greater than or equal to 1 minus 1 by k square. So now we are writing that Chebyshev's inequality, or we can write in this way that using Chebyshev's theorem, this inequality is by Chebyshev, who was a Russian mathematician. Using Chebyshev's theorem we can write that probability that absolute value of x minus mu is less than k times standard deviation, this has lower bound 1 minus 1 by k square, and I am interested in the lower bound of the probability that capital X lies between 40 and 60. So I have to write this probability in this form. So I can write this probability in this form, and then I can compare. I will convert this probability in this form. So now I am using that this absolute value of x minus mu is less than k sigma, that I can rewrite as x minus mu lies between minus k sigma and plus k sigma. So I am writing this inequality in another form, and rest of the things as it is, greater than or equal to 1 minus 1 by k square. Now here I require capital X, therefore I will add value of mean mu for each term. Therefore probability that mu minus k sigma, I am adding mean mu in each of the three terms. Here I am adding mean mu, so I will have x only, and less than mean plus k times sigma is greater than or equal to 1 minus 1 by k square. Now I am having values of mean and standard deviation, that I substitute here. Mean was 50 minus standard deviation is 6.4550. So that I write here 6.4550, or I can simply write 455 sigma into k. This is less than x less than mean mu is 50 plus sigma into k. Sigma is 6.455 k, and this is greater than or equal to 1 minus 1 by k square. Now we are interested in the lower bound for, okay, let me give this number 1. Now we have to find the lower bound. We have to find the lower bound for this probability that capital X lies between 40 and 60. So now we compare this probability or this event 40 less than x less than 60 with this event, or we compare this with left hand side of inequality 1. Comparing, or we can simply write comparing with left hand side of 1, we find that this 50 minus 6.455k must be equal to 40. 50 minus 6.455k must be equal to 40, and 50 plus 6.455k must be equal to 60. So by comparing in this way, we will be able to determine the value of k. Ultimately our aim is to determine the lower bound, and we are doing all this process to find out value of small k. So now I can solve this equation or this equation. By solving both the equations, I must obtain the same value of k. So now from this I can find that 6.455k equal to 50 minus 40, that is 10, and you can see here also 6.455k turns out to be 60 minus 50, that is 10. So we obtain same value of k either using this or this, and that must be same, and if it is not same then we have made some mistake. Therefore k equal to 10 divided by 6.455, and that turns out to be 1.5492. So once we obtain value of k, that we substitute in that inequality number 1, and we are able to determine the lower bound. So now we can see, if I take this value of k in inequality 1, then for this value of k, this left hand side will be probability that 40 less than x less than 60, because we have obtained value of k by comparing this with this inequality. So this is going to be greater than or equal to 1 minus 1 by k square, and that we will substitute here. So now we are considering, or we write that taking k equal to 1.5492 in 1, we find that left hand side is probability that 40 less than x less than 60 is greater than or equal to 1 minus 1 by k square. K is 1.5492 whole square, and using scientific calculator I find that this value is 0.5833. Therefore we have obtained that lower bound for the probability of getting 6's between 40 to 60 is 0.5833. So therefore we can write that the lower bound the lower bound for the probability of, therefore the lower bound for the probability of getting 40 to 60 sixes is 0.5833. So this is very nice problem. We can see that using Chebyshev's inequality we are able to determine the lower bound for the probability of getting 40 to 60. What we have done, first we find out that given random variable is a binomial random variable. Therefore, using the ready-made formulas for the mean and variance of binomial distribution, we are able to decide mean and standard deviation. Then we use Chebyshev's inequality and we convert this left hand side in the form of required probability. Required probability is capital X lies between 40 and 60. So using our knowledge we convert this left hand side in this form and then we compare this with probability that X lies between 40 and 60. By comparing this with this we are able to determine the value of K, and once we determine the value of K, that we substitute here, and this is our lower bound which is required. So sometimes they ask this type of questions to determine the lower bound or upper bound for the required probability, and those type of questions can be answered using Chebyshev's inequality. If they ask to determine upper bound, use this inequality. If they ask to determine lower bound, use this inequality. So fine, I stop here and thanks for watching.